And the next one up is certainly Anubhav Datta. So Dr. Anubhav Datta is from University of Maryland, and who's led a number of efforts, especially in the eVTOL range, publications and not, and maybe, we don't have, okay. Let's welcome Anubhav Datta to the stage.
So I'm an associate professor at Maryland and a co-director of the Vertical Lift Center of Excellence. It's an Army-designated Vertical Lift Center of Excellence. I was also the chair, the founder and founding chair of the Vertical Lift Society's eVTOL Technical Committee. And in that capacity, we created this conference 2 years back. So if you're in VFS, you already know me. If you're not, it doesn't matter. So the vision you have, we all have, requires a lot of high-skilled workers in the future. Where will they come from? So that if you're serious about this vision, you should invest in education and basic research. I didn't see any of that mentioned in the white paper. So I thought I would speak on behalf of all the Rotorcraft centers and generally all the aerospace engineering department, self-appointed. So just to give you a brief background, to remind ourselves why we are here, we want to fly clean and grow commerce. Electric, that's the value and economic impact of electric. But electric comes with a price to pay. We don't have the energy we need for the power level required for VTOL. These are actual hard truth data, some of which we measure in our labs. Well, how much do we need? That's what we need. So 300 watt-hours per kg at a minimum and 3Z. And these numbers are not picked up of thin air. There are sound studies with assumptions and underlying database published that you can read, revise, or refute. And there is institutional agreement on these numbers. So that's the number we need. It's getting hard to reach those numbers using batteries, hence hydrogen. And that's why we created this conference. And I'm delighted to see all the movers and shakers, some of the movers and shakers of hydrogen in this room, thanks to Jesse. And so the goal was you'll all be inside, the doors will be closed, well, they are now, and then we will talk freely and frankly based on hard data. It's still not happening, but I'm hoping in the next few years it's gradually going to happen as we build trust in between these two communities. Because keep in mind, the PMC and hydrogen technology that is for cars is not going to cut it. So our hope is that the unique attributes of eVTOL, low altitude flight, short duration flight, quick turnaround, are going to drive and spur innovators, people like you in the room, and give us the breakthroughs we need in eVTOL. Because unlike in fuel cells, the pursuit of hydrogen is not entirely altruistic. We absolutely need you if eVTOL is to be successful. The data on the batteries are truth data, but the lines are predictions. Who knows whether they're correct? So that's the first barrier you see. There's no systematic research data to validate these predictions. So that's an enormous gap. But there is the promise. VFS is not new to hydrogen. Of course, aeronautics has a long distinguished history in hydrogen combustion, even fuel cells, starting from air environment flight. But VFS is not new in hydrogen either. In fact, the first time Pascal flew his airplane, we credit the first electric VTOL flight to Pascal Chrétien. I remember he sent his report to Wayne Johnson and also told us that 5 or 10 minutes is the maximum he can get. And so we were on it from the very beginning of eVTOL. So it's not something we're jumping onto the bandwagon now. We were always watching hydrogen. But there were problems. The reason we didn't gather the momentum then is because the power density was too low at that time. And so we were watching the investments, basic research investments done by DOE. Now they have doubled. And more importantly, they have almost reached pure oxygen levels. So that's it. You're not going to get any more. So if there was a time to try a demonstrator, it is now. And these are hard numbers. There's no magic behind them. And these are numbers from basic electrochemistry. It doesn't matter low, medium, high temperature, or acronyms. Those are all outer layers. This is the fundamental electrochemistry. And if you want to pursue it, this is the time to do it. But on what aircraft? So 10 years ago, there were no aircraft. But now there are plenty of credible platforms. So we have figured out the motors and the power systems. And some of you, like John Pasecki, is even designing their aircraft together with hydrogen experts. So that was one of the motivations, and we are delighted to have John involved in this, so that people like you can interact with him, who knows how to build eVTOL. But there are problems. If you try to go about designing an eVTOL from hydrogen, the first thing you would need is the power-to-weight ratio. This is the power-to-weight ratio of any fuel cell you can think of. They're unreliable, poorly documented, ad hoc data sets, largely because they have been driven by companies and corporations with no government oversight. The only two reliable data sets are one by Navy Iron Tiger, which is somewhere in there, the UTRC helicopter, and Toyota. They publish regularly. Of course, they protect their proprietary keys. So out of this unstructured and unreproducible data set, it's very hard to design airplanes that are reliable. So I heard several people blaming regulatory committees as introducing uncertainty. Well, do you want to ride an airplane whose power plant is based on this model? Do you want to put your grandma on them? Do you want it to fly on top of your kids' schools? So we have to get our act together also. So I hope in the coming years, when you come here, in addition to cool videos, you would have some hard data, or at least go to VFS and publish the hard data, because from there we can actually move technology forward. This is just the stack. If you come to tank, just in this conference, I heard two numbers. There is 3% for 700 bar storage. I saw 28% for 700 bar storage. I know there are researchers and entrepreneurs here who claim 40%. Well, what is it? So don't blame the regulators. Get your act together, publish your work. Because there's a difference between the Silicon Valley model and aviation. This is not ChatGPT or TikTok that you can push out an 80% solution, get people addicted, and hope for the best. People will die. So you have to be very careful when you design airplanes. As a result of this confusion, NASA funded a small study to build weight models. The goal was, it's out there in open, so you can refute it, revise it, come back your own models, or you can reproduce it. And the software is also free, so nobody's asking for money here. It's a 300-page report with all the information you need, or more importantly, all the information we have as an aviation people. Tell us what is wrong and what we are not understanding properly. And then we can update our models. One of the results of that, those are two big arrows, is that it's clear that there's an opportunity here. These are all the piston engine data, all the aircraft piston engines, the important ones, the black dots. And you can see their power to weight plotted versus power. This is real power. I don't care about gross power. So this is kilowatt E, effective electric output power. Well, piston engines are net power. And you can see that the concepts, the numbers that you can predict with the models, you can meet, you can beat, or you can be worse. So the point is, it gives you a mechanism to calibrate your models. And so we can find out what exactly are the weight trends. It also gives you specific targets. So 1.1, 1.2, 1.5 net power, kilowatt hours per kg, is all you need to beat piston engines. But it has to be the whole system, including the balance of plants. And the model gives you different weight models to calculate those balance of plants. So there's no need to claim 7 and 8 kilowatts hour per kg. Maybe there's an error in the decimal point there, but state of the art is 0.5 to 0.3, as somebody mentioned, and 1 and 1.5 is the best you can hope for. And if not, we'll update the models. So I'll just read it. If there was ever a right time for aviation-focused research and flying a demonstrator to acquire truth data, it is probably now. And I want to re-quote what John said in one of his interviews, that once he gets his aircraft, he's going to test the hell out of it. That's what we do in aviation. That's what needs to be done. But where is the hydrogen? All this big talk. We are in the University of Maryland. There's no hydrogen anywhere. The hydrogen is only in San Francisco and San Diego. So that's not a recipe for a national infrastructure. But there is hope now with the new bill that is taken care of. So at least aviation people don't have to worry about it. And that also gives us a formal umbrella or opportunity to join hands with ground people. You need the demand, we need your infrastructure. But there should be no turf war, because the technology advances needed are separate. So that's one of the problems when we go for fuel cell research as aviation people. NASA says, oh, you're DOE. That's not our prerogative. And we go to DOE, they say, well, this is aircraft, go to NASA. So everybody wants to use the word multidisciplinary because it's a buzzword, but it's very hard to get any support when you are in the interface of disciplines. But they need cheap, we need light, and it's complementary. Whatever breakthroughs we can do together will help both of us. We understand the scope of enterprise is vast, but there is a clear division of labor. You start from production, which is taken care of by the infrastructure law, liquefaction, ground storage, distribution, but the point is all of these will be moot if there are nobody to use that hydrogen. And I submit that eVTOL would be one of the primary drivers of that demand, if we can make it happen with the close cousin heavy-duty trucks. That's why I have clubbed them together. But the point is, the propulsion and onboard storage is very different on the aircraft. So just because we are doing storage and on the ground doesn't mean that technology is transferable to the airplane. They're not. And there's no research dollars on it. So I'm glad John rose up to the challenge, is doing his own thing. Other people are trying to do their own thing, but there's absolutely no research dollars and there's no education dollars. So when John is successful and he will look to hire, it'll be net zero, not the way you are thinking of. There's nobody to hire. Even now, the eVTOL companies call us every other month. They need 100 people, 50 people. Sikorsky asked us for 3-digit workers, let alone Bell. Where is the money? Where are the students? Give you an example. Aviation is continuous use. Nothing in common with long-term storage. Long-term storage, if you talk to the hydrogen experts, the loss is inside. You want to make sure minimum evaporation, no thermal leakage. Continuous use, loss is outside. I keep seeing this wonderful picture of Kennedy Center hydrogen storage. It's useless for aircraft. On board, it's great for on the ground. It's of no use on board. Prevent boil-off. If you ask aviation people, they won't tell you, but the real answer is, we don't want to prevent boil-off. That's how we want to supply hydrogen. That's how our environment flew their airplane. So whether you store it as liquid matters not. In the fuel cell, you want to have gaseous hydrogen. So if things are boiling off, you want to control it with sensors at a rate, so that becomes your supply rate to the engine. So there's no need to break our heads on trying to control boil-off. You need it for 2 hours, 4 hours, it's not a problem. Steel tanks. If you come to us with steel tanks, we're not going to talk to you. We're aircraft people. We love aluminum. You won't talk to us then. You don't like aluminum. It melts fast, fire problems. We love titanium. Embrittlement of titanium, there's no research papers on it. Maybe you have your own secret internal research, but we don't know about them. Carbon fiber, even more unknowns. So all these issues require basic research. And through those basic research, we have to train the next generation. And right now, none of that is happening. But we hope gradually, as you become more and more serious, things will happen. Just a list. There is no data, no basic data, or even consensus on boil-off. As I mentioned, even at 700 bars, I heard 3 different numbers. Well, I heard 2, and there are many more. If you have, those of you who have Toyota Mirai, you know it's 5.4, 5.7% hydrogen storage. But cars are trying to store it for months and months. We don't need for months and months. Hydrogen tank shapes, you can put cylinders and spheres inside the airplane for demonstration. It doesn't work in the long run. You have to put it inside the wing, or if not, you can make the wing thinner. Who is going to do all those studies? Companies don't have the time or the bandwidth. Maybe you can get L by D 12, 14, 16, 20. I'm talking turboprop. Or we have to come up with conformal shapes. Just because people have done it with spherical doesn't mean we have to keep doing it with spherical. We are aircraft people. We don't follow rules. Vibration, no one knows. Hydrogen embrittlement, who knows? Fatigue at cryogenic temperatures, even for Mars, we go only down up to 150, minus 150 or minus 50, not minus 253. Even basic information, like your engine performance with altitude and temperature. It's one thing to fly an aircraft with half an engine, 15 minutes of cruise, but it's another thing to actually have a production aircraft that flies day in and day out at 33,000 feet. DLR has good data. They're way ahead of us, but not up to 33,000 feet. So VFS has a serious paper on workforce, and it's written by movers and shakers of the VTOL industry. I'm not one of them, I just brought them together. So these are the big names in VTOL and aeronautics in general. And I urge you to read that paper. So as faculty, I have to administer a quiz. So tell me, how many liquid hydrogen combustion or fuel cell labs in US academia? Europe, I don't know, but I'm talking US now. Any ideas? Yes. So A+ students here, 0. Let's back up. Forget about aviation, combustion or fuel cell. How many liquid hydrogen labs? Just liquid hydrogen. Doesn't matter for other reasons. No, I won't have put it up there if it were 0. But 1. Yeah, you're right. Yeah, Jacob Leachman has 1. Full disclosure, I have no professional connection with him. I just know he has a wonderful lab, and
just an addendum to the previous one. West Texas A&M, they have a hydrogen combustion laboratory. Josh, your team is working on a hydrogen combustion study.
Okay. Is that related to hypersonics research? That's, what, is it related to hypersonics research?
No, it's for stationary generation, right? We're gonna have gigawatts of electrolyzers.
Stationary generation, okay. Well, still something. So you can pay these people billions of dollars and hope to produce hundreds of students, or this is the conclusion, there's an urgent need for aviation-focused cryogenic laboratories to educate the future workforce. Where will you start? Well, a good start is the centers of excellence. Your government has created for 40 years a structure to educate students for vertical lift. This comes from Norman Augustine's recommendation since the 1980s. And there are 3 centers, but it's just an umbrella. There are 15 schools. These are the people who know about vertical lift. So go to them, maybe invest in them. They have unique facilities, critical mass of faculty. And I'm just showing pictures of Maryland, but it's the same for all 3 schools. Every school has its strength. Our strength is hardware. Any kind of rotors you can think of, from compound to electric tilt rotors to coaxial, US systems, bearingless rotors, they were all invented out of these centers. Even the Mars aircraft, Mars helicopter, has its genesis in the centers of excellence. We make the smallest quad, world's largest quad, everything, and it's all student-driven. VLRCOs are home of the world's highest fidelity tool, at least the US, highest fidelity tools that are regularly used by DoD and NASA. And you can use those tools to find out how much convective cooling you need, whether radiators will cut it or not. I haven't seen any research effort in that direction. And these are well-validated tools. Anyone can run a colorful simulation with the commercial code. The value of a simulation is whether they're validated or not. And these codes have been validated for 20, 30 years using our in-house capabilities. We have rotor rigs. This is the tilt rotor rig that flies up to 200 knots. That's a crude scale 200 knots equal to 450 knots. So if you want to do prop research, want to find out what happens in prop downwash, go and test it here. The blades, the hub, the wings, they're all interchangeable. So flight test is cool and the ultimate proof, but only in a laboratory setting you get the research data that you need. For example, you can do gimbal free, like the V22 or V280. You can lock the gimbal. That's how all the eVTOLs are flying, hingeless rotors. You can take the wings on and off, see how much is the interference loss. All designed by the students. So education and research are at the same time. This is our compound rig. So John showed their compound helicopter design. This is in small scale. It has a tail rotor, it has a main rotor, wings, and these are all students. Even the wind tunnel is run by students. This is a Mach scale test. Tip Mach number 0.65, advancing side 0.3 advance ratio. You can see the tail rotor running. So in research, you do the main rotor, the prop at the back, and you can put the wing wherever you want. And you can see what the downwash and interference. This is just examples. So these unique facilities have been supported by your government, US government, over the last 20, 30 years. So team up with them and do sensible, meaningful tests there. A simple example, in the way academia works, at least on this part of the Atlantic, is that you have to do research that is not tied up with any company directly, because that's our model here. So it has to be pre-competitive, very basic research. So one of the problems we had early on is if you look at a power profile of a VTOL, you need high power in hover. So that's different from cars. Cars need 0 power standing still. Helicopters need maximum power when you're standing still. It also needs maximum power when you're coming into land. That's the difference with airplanes. You don't need any power when you're landing on the airplane. And so one problem was, how do you provide that power when you are running out of power density? So ideally, you would like to have power sharing. Well, it's nice to do it on a picture, but it's not that easy because at the end, the batteries are dying off. And so the goal was, if this is the load, can you use the stack to to charge the batteries in the middle so that you have enough at the end? That way the battery size is also small. So these are the kind of research students do, and it was demonstrated that you can. I remember Joseph Callow came to Maryland, and we got educated through him because we were not fuel cell people. And we identified that this was a basic area, that when you come into land, what do you do? And so that's the solution for that. And the students build their own models and fly. But then it ended because there was no funding to scale it up. And so throughout the VLR course, you would see this trend. There are people interested in hydrogen, trying to do basic research, but then it goes nowhere because they're still isolated individual initiatives. So I would end by saying we need sustained multi-year support to create structured curriculum and research breakthroughs. It takes 2 to 5 years for graduate student training. It takes laboratories for undergrad training. So if workforce is a problem, invest in it. So the key conclusion is we need your support to create and advocate creation of coordinated, sustained multi-year programs. And if you're NASA, don't send us to DOE. If you're DOE, don't throw us to NASA. Get your act together, find out how to, and force us to work together. Otherwise, you'll be paying your favorite constituents, and they'll keep doing the same thing. So I'll correct the title. It's not our needs. We have plenty of things to work on. There's AI, there's quantum. So we'll be happy to work on other things and publish wonderful papers and give each other awards. But it's your need. If you're serious about this future, if you want this workforce, invest on it now. The path to America's future passes through the classrooms. Some of you are from business, some of you are from industry, but you were always all part of academia. So think about it and invest in it. That's all I have.
Yeah, we had to let Professor Datta go first because he's way smarter than I am. That's my theory. So, as Jesse said, I've been doing fuel cells for a few decades now. Been at this for about 26 years. I'm currently Bell's hydrogen propulsion analyst. I've been with Bell nearly 5 years. And I'd like to introduce you all to hydrogen and to fuel cells. We've been talking about them a lot today. And we haven't really talked about what is hydrogen and what are fuel cells. So I'm going to take you on a little trip. First of all, it's an honor and a privilege to be here speaking to all of you. I'm very flattered to be on stage. A little bit about me. I started working on fuel cells in 1996 in the automotive industry. I moved to Aerospace in 2010, working on rim air turbines for Parker Aerospace on Airbus projects. I joined Bell in 2018 to investigate using fuel cells for primary propulsion from everything from UAVs to full-scale aircraft. I've authored a bunch of patents and stuff, and then I met Jesse. And then we did a white paper together with some very smart people in this room. And again, it's been a privilege to work with all of you. A little bit about hydrogen. Let's keep it to the facts. Discovered by Henry Cavendish in 1776. Even I wasn't born then. It's the lightest, most abundant element in the universe. 75% of all normal matter is hydrogen. It's a diatomic gas. That means it's always found as H2. It's not found alone as just H in nature. It's always found as a diatomic gas, unless it's combined with something else. Very low atomic mass of 1.008. It has 1 proton, 1 electron, and no neutrons. And that's going to come up again. Colorless, odorless, tasteless, highly combustible in air. 4 to 74%. It's combustible. Very low density, 0.089 grams per liter at STP, and even at a liquid, it's 0.07 grams per cubic centimeter. Its boiling point in liquid is ridiculously low at 20.27 Kelvin. That's a little chilly. And I like snowmobiling, and I think that's cold. Auto ignition temperature, however, is a very high and stable 500 degrees C. It's more stable than a lot of hydrocarbon fuels. It's got a minuscule 5 microjoules of activation energy. Remember when they used to tell you that your cell phone will catch your car on fire when you put gas in it? Well, it won't. But it's got enough activation energy to light off hydrogen. It's about that much. A positively charged hydrogen ion, it's cation. A negatively charged hydrogen ion is called a hydride. If you want to store things in a hydride, that's what they're talking about. The cation is also called a proton, or an H+. It's low density, exceedingly low density, 1/14 that of air. 0.084 kilograms per cubic meter. That's making storage a lot of fun. Low emissivity of the flame, which means it's nearly invisible. So when it burns, it gives off a faint blue vapor. However, it's got a very high gravimetric density, 33.3 kilowatt hours per kilogram. It's about equal to that of a gallon of gasoline. So when they say that a kilogram of hydrogen is about equal to a gallon of gasoline in energy, that's about right. A gallon of Jet A has about 36 kilowatt hours in it, so it's a little bit richer in energy, but it's about a good equivalent. Very, very low volumetric density at 0.0028 kilowatt hours per liter. That's 2 zeros. It's the smallest element in the periodic table and the hardest to seal. It's kind of a pain, but yet it's also the future, I think. A little bit about fuel cells and what can they do for me. A fuel cell is an electrochemical cell that converts the chemical energy from a fuel cell into electricity through an electrochemical reaction of hydrogen fuel with oxygen, according to Wikipedia. Now, that's a little chalky. A fuel cell, in my opinion, converts hydrogen and oxygen into heat, water, and electricity. That's my version, paraphrased by Joe Rainville, yours truly. Repeat that. A fuel cell converts hydrogen and oxygen into heat, water, and electricity. It's that simple. Pop quiz. Everybody's paying attention? What's the first fuel cell vehicle? It was demonstrated 1959, October 15th, powered by 1,008 alkaline fuel cells, propane powered, 15 kilowatts. Quick. Anybody? Ah, cheater. No, it was a tractor. Ah, you're fired, Monterey. 1959 Ellis-Chalmers fuel cell tractor. Some people know that. That was the first fuel cell vehicle. It wasn't on the moon. It was in a field. So, PEM fuel cells, proton exchange membrane. Remember that proton part? You need to move it through a membrane. So what does that mean? So we're going to hit fuel cell 101 very quickly. It's a solid state electrochemical engine. Has no moving parts inside of it. Converts hydrogen and oxygen into heat, water, and electricity. They're about 50% efficient, which means you're making as much heat as you're making electricity, more or less. So if you want a megawatt of electricity, no problem. You only got to get rid of a megawatt of heat. That's easy. They exhaust water vapor and oxygen-depleted air out the cathode exhaust. Sometimes in an airplane, though, that oxygen-depleted air might not necessarily be a waste product, depending on what you need it for, fire suppression and the like. They operate at pretty low temperatures, 70 to 95 C, or for all of us English unit lovers, 160 to 200 Fahrenheit. They can start up quick, about 10 seconds, even in freezing conditions. They are pretty quick to react. The basic chemistry, they're an electrochemical engine. They don't burn hydrogen, they electrically recombine it into water. Their electrochemical device, the two half reactions, combine hydrogen and oxygen into electrical energy. As we've said, this recurring theme here. The fuel cell, the anode on the hydrogen side is where most of the work happens. It's disassembling the hydrogen. It's reassembled as a water molecule in the cathode, which can be air or oxygen. Your half reaction on the anode is where you take your H2, your hydrogen, and you ionize it down to a proton and an electron. Stripping those electrons off, conduct through the bipolar plate to the next cathode, where the protons conduct through the protonically conductive membrane into the above cathode. So your hydrogen splits in both directions. Your cathode is where the rubber meets the road, where you've got ionized oxygen, a hydrogen proton, and electrons from the following cell to form your water molecule. That's where the magic happens. So your overall reaction is quite simply hydrogen and half an oxygen molecule make a water molecule. Oh yeah, and it makes a lot of current. The theoretical max voltage per cell on a per cell basis is 1.229 volts DC per cell, but it doesn't do that because of physics. So the short version is you get about a volt per cell. If you've got a 600 cell fuel cell stack, you can have about 600 volts at OCV, no load voltage. To produce 1 kilowatt of electricity, you need about a gram of second of air, which is a wonderfully round number, or about 0.12 grams of second of oxygen, which isn't such a round number. You need about 0.018 grams per second of hydrogen. That's going to yield you about 0.18 grams a second of water. You need to manage that water so it doesn't freeze up things. A single cell consists of a pair of bipolar plates because they have an anode and a cathode. You have to have gas diffusion media to allow the hydrogen and the oxygen to reach the membrane on the respective sides. You have a membrane electrode assembly, which is where the protons conduct through. So the membrane's got the worst job. It's got to be gas tight, protonically conductive, and it's got to allow water to move through it. That's an easy job. Then you have current collectors to absorb all those amps and get them out to the world and then back, and a compression system to hold it tight. So the hardware in between is often called the repeating units because it repeats. And surprise, the hardware outside of that, the compression system, is called the non-repeating hardware. I didn't make up these names. It's just what they call them. A fuel cell stack is literally a physical stack up of repeating units. So you end up with more plates, more membranes stacked together. And then you have reactant and coolant manifolds, current collectors, and a compression system. If you're going to size for current, because you've got amp limits on things, you can rate a cell by several different methods. One of them is current density, amps per square centimeter. You've got a given active area. Your active area, determines how much current you can pull. And then how many amps per square centimeter of catalyst on that membrane is your current density, so that gives you your overall current. Most of the automotive manufacturers are typically settling around 1.5 amps per square centimeter. Some companies are a little bit lower, around 1.1, 1.2 amps per square centimeter. Some of the high current density stacks up around 2. The size of the stacks are ranging from about 200 square centimeters of active area to up to 500 square centimeters of active area if you want more current. And so I gave some easy examples here of a 500 square centimeter cell at 1 amp per square centimeter gives you 500 amps. But if you had a 250 square centimeter cell, which is smaller, at 2 amps per square centimeter, you can also get 500 amps. It's all in what you're designed for. Sizing for voltage. Each cell, as I said, is about 1 volt at open circuit voltage at no load, which means you're flowing reactants, but you're not yet pulling current. At full rated power, they're typically around 3/4 of a volt per cell. So a 200 cell stack is going to be about 200 volts at OCV and about 150 volts at full rated power. Need more voltage? Stack more cells. And I gave a couple of examples there where some cells would be at based on various stack sizes, from a small cell up to like a cell at 400 volts. The stack would be at about 400 volts at OCV and about 300 volts at full power. And the current's going to be depending on the active area and the current density. So then sizing for power. God, I love DC. Amps times volts equals power. No square roots, no crazy 3-phase power factor corrections. It's just good old amps times volts. So again, 1 volt per cell, 3/4 of a volt at full power. How many amps are you making? So a 360 square centimeter active area at 1.5 amps is 540 amps times 3/4 of a volt per cell, 540 watts per cell. And if you had 200 cells, that'd give you an 81 kilowatt stack gross, before the compressor, before the water pumps, and before all losses. So this is how you can calculate very quickly full power. Again, you want more power, add more cells, which also increases the parasitics. This is an example of a polarization curve written up by the University of Illinois. This is very generic. You schedule your reactants to current draw. If you do everything right, meaning your temperatures, your humidities, and your pressures, you get good voltage. If you've got bad voltage, you're either too cold, too wet, too dry, or it's Wednesday. They're kind of twitchy. So you don't want to run at OCV because of carbon corrosion. It eats up the catalyst. So you always want to suppress that a little bit. The area of ohmic polarization in the middle where the line's nice and flat, that's where you want to run. Out at the end of the polarization curve, you got transport losses. That means you can't get the goes in as goes out as ins and out fast enough. You're starving for reactants typically, or you're flooding. So in that middle range is where you're really good in an elastic region. The cell's going to run well, but you're more efficient at low power draw than you are high power draw. So you can be higher than 50% at low power draw efficient, but less out at deep current draw. So do you want gravimetric efficiency or do you want fuel efficiency? If you want fuel efficiency, have a big stack making a low current draw. If you want gravimetric and volumetric efficiency, have a small stack and run it really hard, but it's going to use more hydrogen. Oh yeah, hydrogen storage is hard. Well, that's a trade. Maybe we need some of Professor Datta's students to work on that part, because that's modeling. What are the challenges? That's the title of my presentation. The challenges of putting fuel cells in vertical lift, or fixed wing aircraft for that matter, mass and volume, are the primary challenges to adapting stacks to vertical lift and fuel cell systems. Mass, more importantly than volume, in my opinion. Gas turbines range from roughly, these are rough numbers, 3 to 6 kilowatts per kilogram of gravimetric density. A fuel cell stack alone is in the 2 to 3 kilowatt range if you're lucky and you're on the cutting edge new stuff before adding balance of plant. A full balance of plant system is around 0.6 kilowatts per kilogram. That's too heavy. There's things that we can do. Carbon fiber, the freak out of everything. Material changes, things like that. But they're still too heavy, and that's just the way it is, but they're getting better. People are working on it. They're starting to take aerospace seriously. In 2010, when I worked for Parker and said, hi, I want to put your fuel cells in an Aero, click, hello. People didn't take aerospace seriously. They're flying planes now. That's cool. So stack can be orientated standing up. They can be orientated lying down. As long as the water management systems on the cathode can handle it, you've got some packaging flexibility. That's helpful. Hydrogen storage. Hydrogen storage is not easy. I have unfortunately had to dive into it. I am not a hydrogen storage expert. I pretend to be one at Bell because I had to. So where and how to store fuel on board is challenging. It's, in my opinion, the second most difficult part putting fuel cells onto an aircraft. On-vehicle storage has come down to compressed gas, cryogenic liquid, and there's some emerging solid state stuff going on with hydrides. Most mobile applications use gaseous type 3 or type 4, 5 to 10,000 psi tanks. Yes, there's other pressures, but those are the main delineations. 10,000 psi tank stores about double of that of a 5,000 psi tank, but usually there's a mass penalty involved. Your gaseous tank classifications of your gaseous tanks, your type 1s are steel or aluminum tanks. Big heavy ones, think tube trailer. Type 2s are an aluminum tank, filament wound around a cylinder. Your type 3s is where you start maybe getting something you could fly. It's a composite cylinder with a metal liner. I've got a small UAV helicopter with a type 3 tank. It's 3%. The 3% meaning 3% mass of the hydrogen versus mass of the tank. So even a 2-liter tank, it's kind of terrible. Type 4s are a composite cylinder liner with a with a composite liner, which typically means it's a plastic liner with carbon fiber overwrap. Those have a tendency to be a lot lighter than a type 3. Type 5s are a complete composite cylinder linerless. They're kind of funky because they have a tendency to both seep hydrogen and they're kind of on the edge of R&D. But that's pretty much what the options are for gaseous. Taking Quantum's data off of Quantum's website, this is just straight data. What we've got is mass fraction of tank, which is the mass of hydrogen stored for the mass of the tank, and looking at the usable hydrogen capacity. The 10,000 psi tanks have the lower mass fraction versus the lower amount of usable hydrogen. Their bigger tanks, the 5,000 psi tanks, or it's at 350 bar versus 700 bar, generally can store more hydrogen at a higher mass fraction, and some of their production tanks are approaching 10%. That's not the end of the world. And to Professor Datta's remark, we don't have a standard aerospace tank yet. We haven't settled on what's Aerospace going to use for gaseous. Is it going to be 6,000 PSI? Is it going to be 5, 10? Is it going to be 1,200 PSI? I don't have an answer because we haven't certified a tank yet. And this was why I mentioned yesterday that I felt the industry really can work together on what's going to be a preferred gaseous tank, because there are some solutions where they're going to need gaseous, where you might want to park your device and not have it lose fuel over a week. Basically, in summary, lightweight, low pressure tanks are huge, high pressure small tanks are heavy. And this chart is just, again, Quantum's data, looking at a 1,200 PSI tank, a 5,000 PSI tank, and a 10,000 PSI tank. And they literally cross from specific capacity in kilograms per liter and mass fraction. And this outlines very clearly that hydrogen storage is hard. Let's talk about cryo. My management tells me I like cryogenics. It's chilly. Liquid hydrogen is challenging due to the fact that cryogenic storage temperatures are 20.28 Kelvin. That's 20 degrees above absolute freaking zero. Pardon my French. Fun fact, there's 57% more hydrogen in a gallon of gasoline than there is in a gallon of liquid hydrogen. And that still keeps me up at night. 26 years later, it still makes me scratch my head. Probably why I lost all my hair. But liquid hydrogen is 1.8 times denser than a 700 bar, 10,000 PSI gaseous tank storage. So it's the only way you're going to get a lot of hydrogen into a moderately small space, except it boils off. And according to NASA, half the hydrogen that boils off leaves the planet. I don't know, that bugs me. I hate having fuel that I paid for become extraterrestrial. But it's one of the challenges. So you need to use it or lose it. So they all experience boil off of unstored hydrogen unless you have a funky refrigeration system involved in it or other things that people like NASA are working on. But cryogenic storage has the potential to be the most lightweight and compact storage method available. But it does boil off. So if you park your airplane, you're going to start losing fuel. Solid state storage deserves at least a cursory overview. It's maturing. It's low TRL, as Jesse would say. But there's some people working on it. One of the nice things is it's low pressure. Their filling pressure is about 500 PSI. The density is usually approaching that of 700 bar tanks or even that of cryo. They offer 3 times the volumetric density of 5,000 PSI compressed, but they're heavier and they're slow to fill. They've got heat flux issues because they give off heat as you fill them, and they absorb heat as they give off hydrogen. So they're kind of funky like that. They're within 25% of the storage density of liquid at room temperatures in 500 PSI. Weight's a problem. Back to that first challenge of fuel cells. But they have some charm. I don't know if they're going to make it or not, but you have to at least mention them. Thermal challenges. Keeping it cool. Something I probably am not. Hey, here we go. Fuel cells are approximately 50% efficient on average. Again, more efficient at low power, less efficient at high power. And that's just the stack. That's not including any of the parasitics and the balance of plant, and the electric motors and the controllers and all the other fun and excitement. But roughly it's a good number. And they make low-grade heat. Gas turbines cheat. They throw all the heat out in the exhaust. That's just plain cheating in my book. Your typical stack cooling methods are one of 3 known methods that I'm aware of. Liquid cooling, where you have an aqueous-based coolant that must stay pure and non-conductive, or you short out the fuel cell stack. Your current would all go into the coolant and find a path to ground, and that would be inconvenient for trying to power something. It requires a significant amount of surface area to dissipate heat, fin and tube heat exchangers, skin fin, and the like. Air cooling. Large amounts of air are needed to remove the heat, about 4 times more than the amount needed to supply the cathode reactant. So it's going to require a large amount of fans or ram air or some very inventive ways to move air about your vehicle, whether it's a fixed wing or whether it's a rotorcraft. That's a lot of air to move. That 1 gram per second per kilowatt to react, you're going to need 4 grams to move the heat. And it's doable, but it's a challenge. There's an emerging technology of evaporative cooling where they're condensing some of the product water and injecting it back into the cathode. And, well, that's interesting because as a cathode engineer, you wanted to avoid water droplets. And, well, they're using that as a method for cooling, using the latent heat of vaporization and the latent heat of, fusion to cool the stack. So that may be worth investigating. There's companies working on it. So, flying on hydrogen. This is a little bit subjective and has some opinions on it because I'm not a gas turbine engineer, but this has some of my opinions on it. If you want to propel an aircraft with hydrogen, you can do direct combustion in a jet or piston engine. You can electrochemically combine your hydrogen and your oxygen to form DC power in a fuel cell. I'd like to thank Airbus and Ballard for these lovely pictures. Challenges to direct combustion include that low density of 0.084 kilograms per cubic meter. God, that makes storage so much fun. Very low volumetric density at standard temperatures and pressures of that 0.0028 kilowatt hours per liter versus 9.8 for Jet A makes Jet A 3,500 times more energy dense than jet fuel. Makes hydrogen 35 times more energy dense than jet fuel. That's an interesting number. It's just, sorry, less energy dense is what I meant to say. I said more. I apologize. That just means that you need to carry a lot of hydrogen in a condensed high pressure or liquid state. And that's why Jet A is so easy to use. It's 3,500 times more energy dense than hydrogen per liter at STP, hence having to compress it or condense it to liquid. The smallest element in the periodic table, the hardest to seal. I said that earlier. Combustion, and I should say this, on a small gas turbine is an inefficient use of hydrogen and does create NOx due to high flame temperatures. However, I've found that you can mitigate NOx with water injection, and on the bigger gas turbines, maybe it's not that inefficient. So that's a subjective statement, subject for debate. I've been mildly educated on this since creating this slide. Some of the opportunities, though, do exist. The high gravimetric density of hydrogen at 33 kilowatt hours per kilogram is higher than that of Jet A at 11.95 kilowatt hours per kilogram. So it's 2.8 times more energy dense by mass, despite being 3,500 times less energy dense by volume. Welcome to hydrogen. Multiple hydrogen storage methods exist and are being used, such as gaseous, cryogenic, and the emerging solid state. Hydrogen combustion fuel systems, I think, are going to be a heck of a lot easier to certify than a fully electric aircraft. You're 1 degree off of a normal aircraft. Pardon me, I'm part Italian, I talk with my hands. You're only changing one element. You're changing the fuel. So that probably is going to be easier to certify than an all-electric, more electric aircraft that's fueled by hydrogen. Maybe it's a stepping stone. Maybe it's not a bad idea. I don't have an opinion on it because I'm a fuel cell guy. But there's some opportunities. Maybe it makes sense in larger aircraft. I'm not entirely sure. Challenges to fuel cell aircraft. Oh, yeah, there's just a few. Mass. Fuel cells, the good stacks are approaching 2 kilowatts per kilogram, where turbines are 5 to 8 kilowatts per kilogram, only about 3 times more power dense. So your third is energy dense, so we need some room there for improvement. There's a lot of room there for improvement. Hydrogen storage, we've already mentioned the challenges there. Thermal integration. Fuel cells make about as much heat as they do power, and it's low grade. Again, it doesn't get any easier. And it's more complex than a pure battery electric system, except for one thing. Given the mass of a battery system, a typical fuel cell system given the same weight balance can typically go 2 to 3 times farther if you design it properly and beat down the weight. I fully believe that a fuel cell system given the same mass of a battery can go farther, faster, better, with quicker refueling times and less times to recharge. I think it's doable. At least that's what I told my boss. Opportunities for fuel cell powered aircraft. Endurance, 2 to 3 times higher than a battery electric for a similar mass. Multiple hydrogen storage methods exist. Fuel cells are predicted to have a significantly longer service life than batteries or potentially a gas turbine. I'm seeing fuel cells hitting 5,000 to 10,000 hours of durability. When I did a 1,000-hour durability run at General Motors, I was like the freaking hero for the week. My team, it wasn't just me, I had a very good team of engineers and test engineers, and we ran a fuel cell around the clock for 1,000 hours straight. That was unheard of durability in the early 2000s. And now they're doing 10 times that. It's really impressive. If you can double the service life of a gas turbine, then you make a really good point to the customers. And then do you rebuild the fuel cell stack in its entirety in a wholesale swap out, or you just swap out the soft goods? Do the bipolar plates, are they still good to use? So you just have to decompress the stack, replace the soft goods, and put it back in service? I don't know. It depends on how well the stack holds up. So, but they also have significantly reduced NVH, noise, vibration, and harshness. That's nice whether it's in a terrestrial vehicle or in an aircraft or in a helicopter. Fuel cells are quiet and smooth. Zero emissions. I think we all get that. It's kind of nice to give off water vapor for an exhaust pipe. When you hold your hand on a fuel cell system and feel nothing but warm, damp air, even my mom gets that. I had a Chevy Equinox for overnight a couple of days before I got married back in '08. And the one thing my mom wanted to see was the warm, damp air coming out the tailpipe. And she thought that was pretty cool. I couldn't get her to ride in it. Could have something to do with the way I drive. Dad rode in it. And I said, Dad, you want to drive this $4 million prototype? And he said, that's okay, boy. I said, boy, I was glad I worked 2 jobs to go through college so my dad could not drive a $4 million prototype. Love him. Again, I want to thank you all. I forgot to put my contact information on here. My email is jrainville@bellflight.com. Thank you all for your time. Again, it's an honor to be here. I would like to, and it is my privilege, to introduce Gernot Hacker. After studying automotive engineering in 2005, Gernot joined AVL and has been focusing since then on test instrumentation and solutions for propulsion system testing and multiple management positions. Between 2012 and 2018, he's worked in the USA, responsible for expanding the business in areas of electric propulsion system test solutions. Back in the AVL headquarters in Graz, he is now focused on fuel cell technology and correspondingly the test solutions for fuel cell propulsion, also beyond automotive applications like marine, rail, and aviation. Please give me a round of applause for Gernot Hacker.
Thank you. Well, thank you very much, Joe, for the Fuel Cell 101. Now I actually know what our test systems are used for. So what our challenges our customers have, actually. Well, thank you very much for having me today. Yeah, I think it's my pleasure to have the last spot, actually, the most memorable, but it puts a lot of pressure on me, because after 2 days of great presentation, great content, I hope I can keep up with your expectations. So what I have prepared today to talk about is a little bit an intro of my company and the DLR, and I brought a specific project we are right now executing in Germany, which is called the BALIS project, where we are building up a test field for a multi-integration test field for a hydrogen propulsion system for aviation. So talk a little bit about what is the motivation behind it, how the concept looks like, what role of simulation plays in this case, and how the realization goes. And I conclude that. So I think it's not necessary to explain that DLR, the German Aerospace Center, they are partner for us, or vice versa. We are partner for the DLR in this project. AVL as a company, you see in terms of numbers, we are pretty much the same size, pretty much the same age. We also have multiple tech centers and research centers around the globe. At AVL, we see ourselves as an innovation partner. So we try to innovate and bring innovation to our customers in the area of the development, simulation, as well on the testing side for propulsion system. Majorly, we are coming out of the automotive sector, of course, but also we are dealing with many other industries and many other mobility sectors as well. So the core, and this is very important for us, we are a private-owned company, and the owner of the company, which is part of the list behind it, is innovation, and everything what we do, we want to innovate how propulsion systems are developed. So the methodology and the testing tools behind this is part of and core of our business. So in this project, together with the DLR, we really are facing one challenge. So on what we learned, both of us, is that the aviation as well as the automotive industry have a lot of similarities and similar challenges when it comes to new propulsion technology, specifically going into electric flight propulsion. We're talking about hybrid systems, which are pretty complex, and which are already complex for passenger cars, but even more when it comes to safety situations on the airplane. So somehow we need to manage this complexity, and the virtualization is one part of it. But of course also the methodology, how we develop this, focusing on model-based systems engineering approaches, and of course the corresponding test environment to it. And what we learned, of course, you only can get better. And I think during the 2 days of discussion here, we see that only with the right partners, you can, across different industries, you can accelerate your development and really have success. In terms of propulsion systems, I think we talked about it, and we learned now in the 101 session as well what the fuel cell electric propulsion looks like and what it is based off. I think it's needless to say that we see the fuel cell electric propulsion is one strong cornerstone also for aviation, for specific applications in the aviation realm. But, and that's why I wanted to keep this slide also on there, is it's bringing a lot of complexity, because a fuel cell system is always a hybrid system. So you have multiple components, you're adding weight to it, and besides now the weight and the additional components, you're adding complexity in terms of the operating strategy. I think it's very simple. If you have new components and perfectly tested components, they work very fine. But when it comes to degradation of the fuel cell, when it comes to degradation of the battery, and maybe other components, then everything becomes very complex. And how do you manage that in a smart way? And what we see at the moment, there's a lot of work done and development work done on the individual components, when we optimize our stack and we optimize our battery chemistry and so on. And then we couple everything together, put it in the car or put it in the airplane, and then we fly around. So there's a lot of gap in the whole development cycle, where we see there's a lot of inefficiency how we develop those kind of propulsion systems at the moment. So the vision of the DLR and our vision, of course, was to implement an emission-free multi-megawatt propulsion for regional short-haul aircrafts. And this was the vision of the project, and the clear objective was to build the world's first test environment for a megawatt fuel cell-based powertrain for aviation propulsion. So what is the project looking like? So you see here a nice marketing picture, of course. You will see later on it looks a little bit different, the test field. But what has to be installed there is, on the one hand, a liquid hydrogen tank system, because they want to test, of course, also the tank system as for the handling of the liquid hydrogen, also the consumption of the liquid hydrogen, and of course the physical tank as such. Then of course we have a PEM fuel cell. It's not a PEM fuel cell, it's multiple fuel cells cascaded in this case to a power class of 1.5 megawatt. We have a battery, in this case 500 kilowatt, and of course we have also the connection to the electric drive. Most important was that those individual test environments have to be connected to each other, not only on a signal level, but on a true power level. So all the power routing between those test environments have to be ensured. Because the target was, of course, to operate the complete propulsion system as if it would be mounted in the airplane. So you have to take, of course, when you have different test environments like this, you have to take this into account, because you want to have as much as real operating scenarios and conditions as if you would really fly. On the other hand, the focus was the development and optimization of the components, yeah, and the core of it, of course, to develop the control strategy around it. Yeah. There's also no master controller existing at the moment for that purpose. This also has to be developed in this test field. And of course, it should be, and it's a public funded project, it should be basically a breeding ground of collaboration between different suppliers and between different component suppliers in the industry. So there was a lot of firsts for the DLR, but of course, there was a lot of firsts also for AVL. Yeah. This type of multi-integration test bed is something we have done since a decade or more on the automotive area, but we're talking here complete different power classes. Yeah. Now, scaling that to 1.5 megawatt is for us a big deal. So that's why this is definitely a complete new beast what we have to handle here. On the other hand, we bring a lot of knowledge on the hybrid propulsion, but of course also the use cases and the operating scenarios when it comes to flight propulsion is significantly different than passenger cars. So that's also something which is new for us. Liquid hydrogen, I think we heard it several times during the 2 days. It's what we saw is that the necessary peripherals to integrate this into the test field is simply not state of the art yet. Yeah, so there's a lot of new things which are developing, what we have to incorporate, of course. Complex use cases I mentioned already, specifically the switching between those test beds, and I will come to into more detail on that one, also required us to develop new hardware solutions to handle that. Unlike in the US, in Europe, we like compact things. We like compact cars, and we like small apartments. So we squeeze everything in a small footprint. So even though there would have been a lot of land around it, the target was to squeeze the whole test field into very, very small footprint. Yeah. Don't ask me why, but it had to happen. So this was also a challenge for us to package this test environment into a very small footprint. And we will see this later on as well, how we did it. And yeah, the control technology. So there is a comprehensive infrastructure, and this is also something where we had to develop, of course, the control technology to manage all those individual test beds. And of course, there was no master controller, and this is something which has to be integrated. So how does it look like? On the left side, you see an aerial picture of this is a little bit outside of Stuttgart. Yeah? So it was an old military base. It's really in the middle of nowhere, and that's why I mentioned before there would have been enough land there to have space there, but no, we only have a certain lot there in this area, so we had to squeeze everything in. And at the end of the day, it was decided to use this kind of modular building approach. You see the sketches on the right side, doing kind of a containerized solution. I don't like the word containerized so much, because when I tell container, you see shipping container in the port of LA here. Yeah? Those are not shipping containers, so they're modular building blocks, and you will see later on how it looks like. So how does it was set up now? On the one hand, you have the office. The office is basically the operator council. That's where basically the brain of the entire test field sits. The automation and control system. And there's workshop, technical rooms. Then there is one area for the fuel cell test bed. Again, as I mentioned before, this is not one single fuel cell. These are basically two benches of two fuel cell test beds where you have multiple fuel cells cascaded to each other. We have an e-motor test bed in there. We have a battery test bed. And the core behind it, so the spine or where everything is connected, is this switch matrix. So this is where the whole power connections are coming together, and where basically you can switch between different operating and use cases. On the other side here, there's also the H2 liquid storage and the test bed for the liquid hydrogen tank. The containerized solution, or this modular building, allowed us definitely to be very flexible in the integration. And we also could easily realize that also for different technologies in one single test environment. It keeps also to a certain degree the connection paths between those test environments rather short. So how does the flexibility due to this model approach look like? Yeah, so what you see is the focus was to test components individually, but also, of course, connect them and run real load cycles. So there is a hydrogen tank for the hydrogen supply, then you have the fuel cell system, you have the battery system, and you have the inverter. Yeah? In the optimal scenario, you connect all those together. But of course, in other scenarios, for example, you only want to have the fuel cell connected to the battery. Yeah? And this switch matrix behind it, of course, allows to connect those individually together on a signal level, yeah, so the communication level, of course, and also on the true power level. Behind that, there is no operator sitting and switching any gears or something. Yeah, so this, of course, has to be smooth in the transition. So it's all handled by a PLC, which is controlled by our automation and control system. Yeah, so you can, in your automatic test procedures, you can switch basically on the fly the connection between those test environments. Yeah? So we can switch here also different propulsion types. Yeah? For example, you don't want to have a battery, you want to connect directly to the e-machine, yeah? Which is also then connected to the dyno. And a part of that, there is always a virtual component in parallel. Yeah? So we have basically a battery emulator emulating the battery behavior. Yeah? So in this case, we also can establish use cases where, for example, we can manage the degradation of the battery. What happens if your battery is end of life, yeah, or your state of health is not very well? What impact does it have on the complete control strategy then? Yeah, so just a different picture here. As I mentioned, yeah, important is specifically when you have these multiple test environments, you don't have multiple operators. Yeah? So that's why you need to have a controlled environment and automation control system where all those threads come together. Yeah? And then, of course, can also be easily managed. Yeah? So the degree of automation can increase. Yeah? So that you define test procedures prior to your testing, yeah? And then basically can run it basically 24/7 unmanned in reality. So this is, of course, something which has to be created and has to be done. Safety, yeah, safety is always a huge topic, of course, and specifically when we talk about the large storage of this type of liquid hydrogen and the usage of these different environments is a big topic. So there is a central safety PLC, which is monitoring, of course, all the safety relevant functions, yeah, emergency stop buttons, door switches, and so on. Yeah. And of course, those safety PLCs then are connected to a facility PLC, which is basically building the umbrella on top of that. Also very important to get the permits to run this. Cooling, as I mentioned also in the 101, we learned that cooling for fuel cells is a topic. Yeah, 1.5 megawatt fuel cells, it's even more a topic. Yeah, so here there is no standard solution off the shelf available. So what we had to do in this case, of course, because there was also a specific request that the supply water needs to have 35 degrees C. Yeah, so we had to install two specific cooling systems in this case. Yeah. And because of the small footprint, we could leverage that basically in the second store on top of the containers here. So we have here basically chilled water production for 8 degrees C feed and 35 degrees C feed. The anode subsystem, or basically the hydrogen supply, also not very trivial for us. Yeah? Because on the one hand, it is also for us on the automotive area, we're not dealing very often with liquid hydrogen supply. And specifically in this test field, there are distances between the hydrogen tank test bed and the fuel cell test bed. Yeah? And there was also a specific requirement that we are only allowed to have a very small pressure drop between these two, because of course we want to have as realistic scenarios of testing as possible. So therefore, of course, we also had to develop something specifically for that purpose here. The hydrogen supply, how does it look like? So there is the liquid hydrogen tank, where basically you can deliver via trailers to this buffer tank or storage tank. And from there, the liquid hydrogen is then transmitted basically to the testing tank system. Where you have the test tank, then you have the evaporator, and then you go to the fuel cell system testbed. So the task of this testbed is the handling, refueling, and also, of course, the optimization of the tank as such. In total, the hydrogen flow rate, what can be handled there, is up to 120 kilogram per hour. So it also was important here to integrate this as part of the system testing and also how to operate the complete liquid hydrogen supply chain in these regards. There is also the use case, if, for example, there is no test tank available, that we also can run directly, so that there is also connection for gaseous supply available, so that if, for example, the tank is not available, we can run directly from gaseous supplies. I mentioned that before, the digital twin or the simulation part. So in this test field, for each individual system or subsystem, like the battery, the fuel cell system, the e-drive, and the complete propulsion system, there are models behind it. So there is a digital twin, which allows, of course, in real time, to detect certain operating behaviors and certain scenarios which is harmful or which is causing enhanced degradation for individual components like the fuel cell stack or even also the battery. So this is done in real time. So we can see directly if the operating mode is not optimal. It affects immediately your state of health or your degradation of the stack, for example. And this was something which has to be made transparent. In very, very often the cases, people know this very well from R&D, you know your stack degradation very well, you have modeled that, but then of course, how does this happen then in reality when you are in the air? And what causes basically these different effects? And that's something which is done here. The backbone behind it, and I liked very much yesterday's last presentation from the colleague talking about the model-based certification, because that's exactly also our thought behind that you connect, you have a complete chain of simulation and models which are connected also to real hardware in the entire development. So, and therefore, of course, you need to have integration platform. This is something what we have developed in our company, which allows to connect individual models together. If it's the propulsion system model or the flight control and the flight mechanics simulation into one integration platform. And this is connected in real time to the propulsion testing on the physical test bed. So this allows, of course, and on the other hand, of course, also you can use a flight simulator towards also bringing the human factor then into the equation. So this is a concept which is not really new. So we were supplying this specifically in the racing industry, actually. So Formula One teams, for example, they were in the past limited in terms of budget. So for running tests on the track. So they came to us and said, okay, I want to have my car on the test bed, so basically on the propulsion test bed, but the driver at the same time is operating on the simulator. And so this is a concept what we did because it was circumventing a little bit the regulation for the Formula One. And we could show this is working pretty well. So basically the human factor factored in also in the propulsion system testing in these regards. Well, how does it look like today? Yeah, so here are some pictures from the family album. On the left side, the pictures first basically making ground. You see that there is a concrete pad there. That's what was required, of course, to put then the modular buildings, the containers on there. Yeah. Then you see also the containers overnight transport. Yeah. In Austria, this is not a problem, but even though Germany is very close, yeah, there are huge different rules. Yeah, so you are not allowed to drive these kind of oversized transports during the day. So you have to during the night. Yeah, and it's not even it was not even very easy because we were stuck at the Austrian border for quite a while. Yeah, because there were some traffic topics. Yeah, because you define your route. Yeah, and then they have to dismount some traffic lights or whatever. Yeah, so to get through. Yeah, so again, I mentioned Europe, everything is a little bit tighter. Yeah, that's why it's a problem. But it came on site at the end of the day. And the containers are on site, and now we are finalizing basically the commissioning. Yeah. So in our case, those individual modules of this facility is done and pre-manufactured and also pre-commissioned at our headquarters. Yeah. To a certain degree, sometimes we also do certain tests of the facility, and then we split it apart again, those modules, and then we ship it on site and connect them. See the lower pictures. Lower right is the fuel cell test bed, and the other one with the base plate in the middle, this is the e-machine dyno in this case. So that's the current setup. Yeah. As this is also a public project, I think if you find some interest, this is also something you can visit. So we are allowed to bring customers or people there who want to see this test field. So this is available basically. So at the end of my presentation, I want to conclude. I think I'm a strong believer that fuel cell propulsion will be the future for aviation. I learned myself that the aviation and also the automotive industry, we share a lot of challenges in this case. And what we find, of course, how to manage these complexities simply via virtualization and model-based systems engineering. And the best environment to have also validated data, what we heard before from the university, is definitely having these environments available. And this multi-integration test environment is one example, which could fill the gap between R&D and kind of component optimization, and then already flying in the air. With that, I want to conclude. Thank you very much for your time, and open for questions.
One question I didn't answer for Jesse was, what does the HyperLab stand for? And it's not my personality. It stands for Hydrogen, Propulsion, Experimentation, and Research. And yes, I made that up myself. But that was the first thing I did at Bell was immediately, during my interview even, I said, we need to open a lab. And they said, okay. And they asked me if I could spend a lot of capital by the end of the year, and I said, if you let me. And, well, they did. Anyway, any questions from the audience?
So it seems like from the last session of presentations, there was a call for the need of greater mass support for educational initiatives, from the need of providing a greater means for resources in academia and schooling to simply educating the general public on hydrogen-based fuel. So my question to you is, other than the obvious difficulties in hydrogen storing and handling, what do you think are the reasons why there isn't more widespread and, more importantly, public support for hydrogen? And what things can we do to address that and move towards a greater public acceptance and, more importantly, support of hydrogen?
Who's that aimed for?
I guess any one of you guys.
Well, I mean, hydrogen has not been mature enough in terms of weight and thermal to be on an aircraft for a long time. And the impetus, the drive has been from environmental concerns. And in the US, we can't even agree on whether it is real or not. So there's a two-pronged approach in terms of educating the public. HS teaches a class with data, so you can make up your mind. But on the R&D side, it's a different story, and we are still trying to motivate people to invest in it in aviation.
I have a slightly different take on that coming from the industry side. As I said, I've been doing this for 26 years, trying to put hydrogen in cars and airplanes. A lot of it came down to cost, that it was too expensive to put in an automobile. Several large programs have been canceled because the companies couldn't afford to do them at such a loss. The two current fuel cell vehicles that are in production, the Nexio by Hyundai and the Toyota Mirai, probably cost as an estimate 3 times more than what they're able to sell them for. And I think that's really limiting the widespread adoption to hydrogen. And then, as Anita said yesterday, hydrogen's like $24 a kilogram. Ouch. So it's going to come down to not only regulatory acceptance and getting things straightened around there, but we still haven't been able to bring the cost out of the systems, much as less the fuel.
Well, just from comment from my side, I think I cannot say that at the moment there is not enough investment and also not support from entities. I think it's regional differences. Yeah, of course, what we saw before, this test field in Germany, this is publicly funded. Yeah, so there is a lot of money put into this at the moment, and I think a couple of years ago or decades maybe, the stars didn't align. Yeah, and now of course we see all the stars aligning for hydrogen. Hydrogen becoming the common denominator amongst a lot of industry. Yeah, it's not only the mobility sector, but it's also industries like chemical industry, steel industry, which is focusing on hydrogen. Yeah, and we see large countries like India, for example, having a very, very clear roadmap in order to become energy independent. Yeah, and hydrogen plays a significant part of that. Yeah, and I think as soon we have enough hydrogen there, either it's green hydrogen, blue hydrogen, whatever, then everybody will follow, because you need to have first the fuel and then use it. But this is happening right now as we speak, and therefore I think there's no path backwards.
Thank you. My question is about AVL testing facility. I'm abroad from Airbus. On your process schematic flow diagram, you had a liquid hydrogen storage tank and test tank about 200 kg capacity, and the filling rate was about 120 kg per hour. Any specific reason? Because this is about 1.5 hour fill rate for a 200 kg tank. So what was the rationale actually for keeping that quite low filling rate?
Yeah, so I think the specs what you saw on this graph, of course, I think they're not the latest ones. Yeah, on the one hand, and there was no specific reason for it. I think this was more that these are the components they had available, and they're planning for. Yeah, so this is definitely a matter of change, which definitely will evolve during the setup of the test field. At the moment, that's the specs because they have a test tank and components which are available. I think this was the reason why those specs were set. Yeah.
And from a liquid hydrogen storage tank to your test tank, the flow of liquid hydrogen transfer line, is that pressure-fed system or is that a pump-fed system you're actually considering?
A pump, as far as I'm informed. Yeah.
This question is for Professor Datta. I have the opportunity regularly to serve as a remote mentor to my alma mater. That's Virginia Tech. I get reached out to when undergrads reach out to me. It's largely because they see I work in aerospace. They want to have an idea what that's like speaking with a practicing engineer in that field. If one of these undergraduate students reached out to me and said that they really want to get into eVTOL and fuel cells, what guidance would you recommend I give them? Should they go into Aero? Should they go into chemical engineering? Should they study chemistry? What would your ideal candidate be that you want the industry to recruit?
There's nothing more grander than aeronautics. So what we find, and it goes up and down with Hollywood movies, Elon Musk, But what we have found is out of all our graduate applicants, more than 50% are now from chemical engineering, computer science. Mechanical has always been a constituent. So many people want to have a broad-based undergrad and then move into aerospace. And particularly now, eVTOL is very hot. Usually they don't listen to your advice, so they will do what they want to do. But that's one of the trends that we have found.
If I could add a little to that, as somebody that interviews candidates and people from my lab, over the years we've found that, in all honesty, mechanical engineers are incredibly flexible. And if they have a master's in aerospace, that would be really bonus. We've had aerospace and electrical engineers, and they're all very talented. But the mechanical engineers seem very resilient. For some reason, they just like weird challenges. Whether it's a mechanical issue, it's an electrochemical engine, but it's being fed by pumps and fluids, and it's a fluid mechanics problem and heat transfer problems, and all of that. And then the DC electrical doesn't seem to scare people so much as when you're trying to do three-phase power calculations and all that. So we've had very good luck with mechanical engineers over the years. But again, I wouldn't shy away from electrical or especially aerospace engineers, but the only aerodynamic part of a fuel cell is the turbo compressors and turbo pumps.
Generally, I would say they want to be part of something larger than themselves and then just getting a job. So that there is a lot of job in this field doesn't excite them. So that's why aerospace and now energy is a key driving factor for them.
I got one more question about the test facility. I'm a bit curious about your experience about actually taking this project through planning, permission, and permitting process. How was that experience? Any learning lessons learned, or any experience you would like to share?
Yeah. So I think the permitting process in this specific case was not so complicated because it's far outside the city. So it's on this military base. So from that perspective, it's a closed environment and it was easy. We do, though, have a pretty good experience at Aerospace for that because we are operating also our own test field, specifically for fuel cell testing. And our headquarters is based in the middle of a city center. So we have in direct proximity housings and people living. So there, it took us almost 2 years. Almost 2 years to go through the complete permitting process. It wasn't so much the lab as such, but it was the hydrogen storage. So at the moment we are running out of trailers, but we also needed to get the permit for a liquid hydrogen tank. And there, of course, we had to do a lot of teaching and consulting, of course, also of the authority, because they don't have a clue. They just are afraid of whatever, which is not, sometimes nonsense, but still you have to prove a lot of things. And during this process, of course, we have developed quite some knowledge, how to handle this kind of base permitting process, knowing, of course, every local authority has different rules sometimes, but I think if you come with a certain base knowledge and base technology, ensuring and proving that you have a safe environment. For example, we also got a TÜV approval for our safety chain, what we are also providing for our test beds for our customers. Once you have this stamp, the discussion is much easier. But yes, there are many things which have to be considered. If it's lightning protection, if it's specific cameras, of course, heat detection cameras, because if hydrogen burns, you don't see the flame, it's just very warm. And on the other hand, of course, there's a fire suppression system, of course, which has to be in place then. We also, sorry, I want to add on that, but one aspect was also because of we are very close proximity with housings. We had also to show simulations because we have a hydrogen vent, and we had to basically to prove what is the rate of hydrogen which is allowed to be emitted from this vent. We had to do simulations of wind, moving basically the hydrogen cloud to
towards a balcony because there was this threat. Somebody is standing on the balcony smoking a cigarette. So we had to basically, based on the simulation, show and prove that only a certain amount of hydrogen is allowed to be emitted. Because when the wind comes a certain direction, of course, to this point, there is no ignitable mixture anymore. So all these kind of things have to be considered.
That's a new way to detect hydrogen I didn't think of.
Yeah.
Oh, the room's clear.
But it could happen. It could happen. And people have a new haircut then. I'm not looking at you. Sorry.
Ow. Hair Club for Men called. We're looking for donors. Just saying.
Staying on the hydrogen facility, what's the value proposition of a modular lab like the one you're suggesting? In a private business, why would I look to adopt that modular? Is it the safety you just explained?
You mean the container solution?
The container modular solution, yeah. Like why? What's the unique value proposition, or vice versa? If I am to build my own ad hoc within my own business, what are the pain points that you see customers, your potential customers, coming up to you and saying, solve this for me?
So first of all, a containerized solution like this one, is not cheaper. It's, I wouldn't say much more expensive, but it's slightly more expensive. What the difference is first of all timing, because when you start building your own building, at the moment, due to certain economical situations, you don't know at the beginning when is the building ready. You have delays. You have to manage many suppliers because there are plumbers, there are guys doing the walls and whatnot. So you have to manage this project, of course. So it's very complicated. And at the end of the day, when you start building today, you don't know what is the cost at the end of the day. When the building is finished. It's as simple as that. And with a containerized solution, it's much more plannable in terms of cost, what it will have at the end of the day, because that's what we quote you, it will cost at the end, because that's what you pay us for. And second, of course, we are able to plan the finishing of the facility much easier, because the modules, as you saw it, they are pre-manufacturing in our factory, and then basically they are brought on site, and the work on site is really limited. So you saw this it's a base plate what was put in there, or a concrete pad, and of course you need to have facility connections, power connections, and so on. But from that perspective, it's much easier to do that.
But most of the times the bottleneck isn't the actual lead times on the plumbers and the electricians, it's actually getting the permits. At least in California, that's the experience. So it's the idea that it's standardized enough that nearly on day one I can go and submit my planning and then building.
It helps, yes. So it helps on the permits, correct? It helps, but still you need to go through a permit process. So that's I wouldn't say it's a little slightly different, because you can also argue sometimes, because it's a modular building, you can move it, so it's not a fixed building, So and then of course you can sneak around a little bit in this permitting process, but still you need to have a permit, But yes, this helps sometimes, There was also sometimes the argument that people think, okay, now I don't know exactly if I stay at this facility or at this place for very long, And then basically, of course, the investment into that is easier because you can move it, You can move it then on somewhere else again, In reality, once you have installed it, it's not going to be moved. That's the reality what I see from customers, But it's a good marketing point. I'm trying to sell that, Okay,
ready? Question? Okay, for the BALIS facility, it's really remarkable. It looks fantastic. Did I miss, the cost of what that facility is going to be? If I wanted to organize and build one for my own, how much, rough order of magnitude, how much would it cost?
So I don't like to talk prices, of course, on stage. So to be honest, it really depends. In terms of what are the use cases, what are the scenarios you want to test, what are the different test environments. But we are talking here in this what I showed you here. So roughly in an area of 10 million, 15 million, or something.
Yeah, so that's basically the area where we're talking. But this is top notch. Yeah, we're talking other multi-integration test fields. Yeah, where we're talking maybe 1 or 2 million, something like that.
You said 10 to 15 million?
In this specific case, yeah, in this specific case.
Okay, great, thanks.
I have a kind of a question about economics. Joe Rainville, you made an interesting comment that the fuel cell powered car is about 3 times as expensive, roughly, right, of a regular car. Well, that's actually kind of good news because a turbine powered car will probably be 10 times as much. So there's a couple ways of looking at it. So with your automotive experience, I think that brings a good perspective. Could you talk about what the driving costs are for fuel cells? And manufacturing technology is places where you can get orders of magnitudes improvement in cost. You know, it's amazing. An automobile, as complicated as it is still like $10, $12 a pound or something like that. Could that be brought into fuel cells? And there's a chicken and egg problem, I understand. And what is in the fuel cell that drives the cost? Is there manufacturing methods that could bring that down? And if there's basic research that has to be done, Professor Datta, I'm sure, would be able to like to help you out on that. So, general about the economics, if you could tell us about that.
I will do my best to answer that. My first year and what became the GM program was in the Delphi stack team. And that's where the money is. It's all about the stack. Because everything else outside of the stack is the care and feeding of the stack. The air compressor is expensive because it's air bearings, usually in high speed, approaching 100,000 RPMs. But really, it's all about the stack. Platinum. Back in the old days, Jesse and I laugh because it used to be 0.77 grams per square centimeter of platinum. And now I think they're, what, 2 orders of magnitude less than that? Yeah, it's like sprinkles of platinum. The membrane electrode assembly is a perfluorinated sulfonic PTFE, thank you. Yeah, it's a freaking polymer that conducts protons. And I had to pull those slides out because of time to get through this, but I could have done Fuel Cell 101 just on the membrane electrode itself. It's a protonically conductive membrane. It's an ionomer, and it's not cheap. It's cost. Some of the material base cost is fairly expensive. Stamping bipolar plates, which sounds simple, they're very complex geometry and very hard to stamp to get all of the geometry that you need for flow fields, for conductivity, because you don't want contact resistance through the various layers, and then the gas diffusion media to allow gases down to the catalyst layer and allow water to travel up. It's all in the materials and the science. Now, it's gotten a lot better. In the early days, we received a Ballard stack when I was a young lad, and we were walking it on a cart. We had a gentleman pushing this cart, and we had a guy on each side of it. I was one of the guys because that stack was $4 million. It was a god-awful expensive stack. And now stacks, you can buy a Ballard stack, I don't know, in the tens of thousands of dollars. But a gasoline engine is $10,000 for everything. Now, you bring up the point of aerospace. A gas turbine for, 400 kilowatts is probably around $250,000. So it's a much higher price point. And that does help, but we still have to cover for that gas turbine, the electric motor, the controller, the fuel cell system, hydrogen storage, and a thermal system. And that does get expensive. So it helps a little bit with the economy of scale as compared to automotive. Now, right now, one of the things I can speak to is publicly known that Honda and GM have a joint venture. They brought all their best and brightest into one program to try to squeeze cost out of fuel cells. GM's invested zillions of dollars in fuel cells, and they're still not able to get them cheaper than an IC engine. And they can project scales of volume. I mean, they made 150 fuel cell Equinoxes just out of sheer force of will, and they were expensive. They were millions of dollars. Now they could do that for hundreds of thousands, but they're still not going to be that cheap. Battery electric vehicles, an electric pickup truck is somewhere between $60,000 and $100,000, and it's just got freaking batteries in it. So they've got to amortize the cost of the electric motors and get those powertrains down where they're a commodity. It comes down to that some of the base materials are expensive, some of the metals are expensive. Platinum's still not cheap, even though they're using a small amount of it. And even with mass manufacturing, the automotive manufacturers haven't been able to get fuel cells down to where they're cost competitive, even with the might of Toyota. And, you know, they were always looked at as the gold standard for manufacturing efficiency. So if it was easy, we'd all be driving them already.
As we're winding things down, I think I've got a question or two, if I could, on the panel, and then we'll wrap up, certainly.
You're the chairman, dude.
Okay, thank you, man. Okay, so let me start to left and then move to right, or vice versa, probably from your perspective. I'll start over there. And what I'm saying is, I think that, and just take a step back, for those who don't know, or haven't done work with AVL test stand, the second largest building in the U.S. is the Chrysler Building, after the Pentagon, right? And if you realize what is underneath there, actually there are motor tests now. I was a diesel, I was on the dark side before the fuel cell. I worked on the diesel engine. And there are, I don't know how many, 20, 30 test stands. They're all AVL. But you guys have done a lot of this work in conventional, I'm not trying to get into advertising, I guess I am. The point is that Move Node of Fuel Cells, as you know, worked at Fuel Cell Labs. We see this really scale, and what I'd like to repeat what we just saw is we saw a hardware in the loop, an individual testing, a software in the loop, and a simulation in the loop. And all of that together, and you ask, we heard from Anubhav, and we don't have even some of the basic test stands like this in the US, but what is the magnitude of this test stand to the development of the fuel cell hydrogen propulsion for aerospace? Is this all we need? What is the magnitude of this test stand? What are we going to get out of it?
I cannot tell you if this is all what you need, but I tried to mention it. For us, when it comes to testing and development methodology, we saw clearly in terms of testing environments which are available currently and what is in the industry, there is a huge gap. There's a huge gap between now component testing and in this area where you have something, although you also see a lot of do-it-yourself kind of setups there. And then there is long nothing. And then, of course, you have the true hardware testing in the vehicle in the area. So we strongly believe that this type of test environment can accelerate the development cycles significantly, because you can cover a large percentage of what you would do in your demo vehicle or in your demo airplane already on the ground. So until you get basically to your vehicle, you already have figured out the major problems what you will face in the air. So definitely I see that this type of testing environments, and it's not only the environment, because I showed you some nice pictures of containers and whatnot, but it's also the methodology behind it, how to use it, and how to integrate this development process and apply it, of course, which enhances then the way we can accelerate. And I think that's the key behind it. It's on how do we do development. Testing environments, it's a testing environment, but it's the methodology behind it which counts.
The reason why I mentioned the diesel test stands is there's multitudes, tens of them. Are we looking? Is that something you have one? So which is you have one of them is a very good development tool. And then the other one could be a durability. So it looks like you're trying to develop first and then get durability later, right?
Yeah. So this kind of test environment is not a durability test, not at all. Yeah. So I don't foresee that you need many of those for a development program.
Right.
Yeah. So this is definitely not what I see. Yeah. We are facing that also in the automotive realm, where we use this type of test beds, of course, and we see a decreasing demand of this type of testing facilities, because there is, you only go to this type of test field for a specific type of tests, of course, when it comes to complete propulsion system. As soon your models are validated and everything, you can front load a lot of stuff already. So then, of course, you are again in your component test area and so on. So I don't foresee that this is the only test field which is capable of doing that. So but it's part of it. Yeah. So it's for me, it's never one or the other. Yeah. It has to be the complete testing chain. Yeah.
Powertrain, the whole powertrain chain.
The whole powertrain. Yeah. And also the individual development environments. Yeah. Because in your development, you have different, to a certain point in time, different environments you need. Yeah.
Different hills until you have the whole system. Yeah. Okay. And then going to the industry and academia, what do you, without, you don't have to say anything confidential, but what do you think is needed on test stands on this side of the pond? And
Well, for us, you need to do validation of your concepts, right? If you want to fly something unique from a UAV up to full-scale helicopter vertical lift device, you have to prove your electrical architecture, your system architecture, and you need a test stand that can do that. And you need a test environment that can do that. So eventually you're going to need environmental testing, you're going to need altitude and all that. But you first have to lay out your basic architecture where are you going to run your fuel cells in series to get high voltage? Or are you going to run them in parallel where current gets froggy and starts going in places you don't want it to? How are you going to manage from the fuel cell current?
you just said froggy, right?
Yeah, froggy.
Okay, just check.
That's a technical term. Look it up.
Okay.
Where current gets to be, current moves in unexpected ways, Jesse, and has a tendency to find ground in areas that are not quite where you expected, which is a technical term for froggy. Yes, look it up. I'm going to write a paper about that.
Okay.
And so anyway, once you've got your basic architecture figured out and a controller for running, if you're running multiple fuel cells, which we probably will for a larger device, and you have your electrical architecture tested out in a laboratory environment, you're then going to have to do environmental simulations. And then trying to take all of these iron birds and put them in altitude chambers is what I see as the next step. And that altitude chamber could be a full powertrain simulation where you've got everything from hydrogen in, could be the tank even, right up through to the heat rejection system and the rotor. And that rotor could be powering a dyno or it could be spinning a real rotor. So it's going to be various steps. And then as you mentioned, durability is a whole nother animal. Once you've got it figured out and it works at altitude and does everything you want it to do, then is it repeatable?
So I'd encourage everybody to read about how the XB-15 was developed. That's a poster child of how a new kind of aircraft is to be built. So in short, recommend DoD take charge of this because they understand aviation, bring academia, industry together, and build an aircraft around the fuel cell. Retrofits we have done many, many years back, and that doesn't work ultimately. Sit in one room, design out a whole test program, involve NASA, university, and then create a demonstrator, prototype, fly, and make sure that that data is available to everybody for peer review and validation.
Do you think a test stand like BALIS would be beneficial in one of those organizations you mentioned?
I don't know about BALIS, so I don't want to comment on it.
I meant a test stand for fuel cell powertrains.
Yeah, of course.
Yeah.
Scaled test stand. You can't just cook up stuff by putting them together. I mean, that might work for cars, but not in aircraft. You have to have a Mach scale or fruit scale model. There are national facilities like TDT where you can simulate both. So people have to sit down, design out a program. I see Lieutenant Colonel in the Air Force in the room. Not STTRs or SBIRs. Those are short-term infusion of, that doesn't cut it. Have a 5-year, 10-year, long-term program. Again, there are books, NASA reports, see how XB-15 was developed. Took 10, 20 years, they got it done. That's how you should do it.
Okay, last round for questions in the crowd. Okay, I'm going to do a short wrap up, but first we're going to thank the speakers. Excellent.